first Newton's law. An object in motion, so it's statement, at a constant velocity. So motion at a constant velocity. So when you say constant velocity, you know that acceleration is equal to 0, okay? So when you say constant velocity, automatically acceleration is equal to 0. Motion in at a constant velocity or remain at rest unless acted upon on by an unbalanced force. Oops. Unbalanced force. Unbalanced force. So unbalanced force is the sum of all the forces. So when you say unbalanced force, so this is just the sum of all the forces acting on the object. Okay, so sum of all the forces. So it's very important that you're taking the sum. So you're not only talking about a single force here, you're taking the sum. And inertia is actually just defined as the tendency of an object to resist change in motion. Okay. So change in motion, either moving or the object is at rest. So if you have this particular case here, Fa, if this is equal to that, well, if this is moving, velocity is to the right, for example. So in this particular case, this is moving with a constant velocity. Okay. So if this is equal to this, so it should be moving with a constant velocity. Again, acceleration is 0. And on the other one is the object is at rest. So this magnitude should be equivalent to this magnitude. So in this particular case, velocity is 0. V is 0. Well, same thing as the acceleration is 0. Okay. So this is at rest. So when V is equal to 0, the other way of saying that one is that the object is at rest. Okay. So an unbalanced force can change the state of motion of an object. So the state of motion can be at rest. So you can have the object would be at rest. It could be accelerating, or moving with constant velocity. So state of motion. So when you say state of motion, state of motion could be at rest, accelerating, or moving with a constant velocity. So Newton's first law implies that there is no difference between at rest and constant velocity. Okay. And in equation form, this would be given as F net is equal to 0. So mathematically speaking, this is your first law. Okay. So the net force acting on the object is 0. Okay. So the net force acting on the object is 0 if, again, the object is at rest or moving with constant velocity. So automatically, if the object is at rest, the net force or the sum of all the forces acting on that would be equal to 0 to take the sum. So just like in the previous example, you have at rest on the rocket lying on top of the Earth surface, and you have the car moving with a constant velocity. So for both cases, the sum of all the forces is equal to 0. That's why right away, I would say that FA here, the magnitude are the same, as well as here, the magnitude would be the same. So the magnitude of their forces should be the same. So use Newton's first law to explain why people are injured in car accidents when they do not wear seatbelts. Well, without a seatbelt, remember that initially, if you're moving at 100 kilometers per hour, your velocity is the same as the velocity of the car. But once the car is being stopped, if you have a barrier, well, if you have a car here, initially moving at, let's say, so you're driving inside the front here. Then you have a, let's say, barrier somewhere here. Okay. If it hits that barrier, okay, if it's at that barrier, the car will stop. But since due to inertia, it's just a property of objects, you will be moving outward. Okay, because of your inertia, you tend to move forward. Okay, and that could be devastating if you hit the windshield, or if you have here another layer of, you hit that particular barrier. So that's the reason why you need to actually have your seatbelts on, especially in highways. You're moving relatively at great speed. Okay, so let's move on to the second one. So the second Newton's law. Sometimes books call this one as law of force and acceleration. So when an unbalanced force acts on an object, so now there's an unbalanced force. So this tells you that F net, the sum of all the forces, is not equal to 0 in this case. The object will be accelerated in the same direction as the unbalanced force. So your object, if the net force is not equal to 0, again, you have acceleration. So in this case, another way of looking at this one, acceleration is not equal to 0 in this case. This force is the product of mass and acceleration. So if you can see here, we try to get the expression. This sum of all forces is just the same thing as your unbalanced force. Again, that's the net force. And yeah, so using this notation here, summation of all the F, that is just MA. So that's the famous equation, F equals to MA. But make no mistake, that sum here, this is not just a single force. Well, it can be a single force, but again, you're taking the sum. So that's why, if you can observe, the drawing of your free body diagram is very important in this case. So summation of all the forces is equal to MA, mass times acceleration. So the unbalanced force is also called the net force or resultant force. Net force is the sum of all the forces acting on the object. So again, you're talking about net forces here. So you're taking the sum, okay? Hopefully you try to familiarize that one, that in this case. That is why instead of just placing there F is equals to MA, it's relatively important to use summation of all the forces, or you can actually use F net is equal to MA. Either way works. So if you use F net, tell you the sum of all the forces and equal to 0. So actually we got the definition of Newton in this case. Again, 1 Newton is just 1 kilogram meters per second squared. So a Newton, therefore, based on the definition of a Newton, it is the force needed to actually move or accelerate a 1 kilogram object by 1 meter per second squared. So a Newton, if you can apply 1 Newton of force, okay, if the net force acting on the object is 1 Newton, and that object has a mass of 1 kilogram, you would expect that its acceleration is 1 meter per second squared. So that's the definition of a Newton. Okay, again, some of the forces, you can get different forms, but we can see net force is equivalent to that. You're taking the sum. So you could have, well, in some cases, you can have one force, but in most cases, you have more than one force. So just remember that. And a force is a vector quantity, and the unit is Newton. So therefore, you have to remember how to add vector quantities in this case. Okay. So force is a vector quantity. Again, we say that it has both magnitude and direction. Okay, it has both magnitude and direction. So make no mistake that it's a vector quantity. So you will be using the direction of this force. So what is the base unit of the second Newton's law? Again, we already discussed this one. 1 Newton is just 1 kilogram meter per second squared, and its definition of a Newton. So a Newton is just the force needed to move a 1 kilogram object by 1 meter per second squared. Okay, let's take this example number 7 here. A 1.00 times 10 to the power of 3 kilogram car accelerates at positive 1.5 meter per second squared. Determine the net applied force. Okay, so let's say, for example, I use the, well, it doesn't specify if it's moving up or to the right. Let's just say the car is moving to the right. So I use to the right as my positive direction in this case. So I'm going to write my given quantities here. Mass is 1.000 times 10 to the power of 3 kilograms. And then the acceleration is positive 1.5 meters per second squared. We want to know the net force, F net. Okay. So the net force could be, again, could be consist of more than one force. But anyway, in this particular question, we're just being asked to get the net force. Okay. So for our solution, well, you have acceleration, you have mass. So you can just use the second Newton's law, ma, and solve for the accelerator or for the F net. Well, you just have to substitute your mass, 0.00 times 10 to the power of 3 multiplied by 1.5. So 1.5 times 1, this would give you an answer of 1.5 times 10 to the power of 3 newtons to the right. So again, if you can see, since net force, this is vector. So even though you're not explicitly being asked to solve for the magnitude and direction, but since the question is the net force, and net force is a vector quantity, so you need to give both magnitude and direction. Okay. So still, in some cases, some of you still don't realize this one. Like velocity. Velocity is a vector quantity, so therefore, the final answer should be given in both magnitude and direction. Okay, so let's take the second example number 8. A force of 350 newtons to the left, or the direction is left, is applied to a 75 kilogram box. Determine the box acceleration. If the box was originally at rest, what would be its velocity b, or what is velocity b after 2 seconds? So for letter A, the acceleration, well, you're given F net It's 350 newtons to the left, okay, and the mass is 75 kilograms, and then A is question mark. However, right away, remember that based on the second Newton's law, whatever the direction of the net force would be the direction of your acceleration also. So therefore, this direction is left. So without necessarily solving it yet, I already know that the direction of my acceleration is left. Again, the reason being is that since the net force is directed left, so the acceleration is also left. So if I'm going to use my second Newton's law, F net is ma. So A is just F net over m. So F net is 350 newtons, and then A is mass is 75. So A would be, so this is now the magnitude, and automatically, since I'm using the standard units or the units, mass is in kilogram and the accelerator or the net force is in Newton, so automatically the acceleration is also in meters per second squared. So this would be 4.7 meters per second squared. And again, without necessarily having that part of the computation right away, it's to the left because of, again, that's to the left there. So according to second Newton's law, again, the direction of the net force is the same as the direction of the acceleration. So therefore, it also applies. If the direction of the net force is left, so the acceleration is also to the left. So for the second question, this is where your learning, or at least what you ever know in your kinematics, because letter B is a kinematics question. If the box was originally at rest, what would be its velocity after 2 seconds? Well, you would assume that if the net force is constant, this acceleration is also constant. So that means that 4.7 meters per second squared to the left. We're given that, okay? And it is originally at rest. So initial velocity is 0. And we're given a time of 2.0 seconds. So in this case, you can express this one as negative 4.7 meters per second squared. So to solve, remember that the displacement equation that we use in kinematics, that would be applicable here because this acceleration would be constant. So therefore, we can use, I think one of the equation there would be V is equal to VI plus AT. So in this case, this is 0 plus negative 4.7 times 2. So the velocity after 2 seconds, so that would give me negative 9.4 meters per second. But then again, in terms of direction, 9.4 meters per second, that would be to the left. So the answer is that. So this is the case wherein you, again, letter B is a kinematics problem because velocity is a kinematics quantity. But since acceleration is part of the second Newton's law, you can use that information. Again, if the net force is just constant, which is things that we'll be dealing with, that particular force being exerted on an object is the same all throughout. So we would say that the acceleration is also the same. Okay, let's take this example here, and then after which we'll have a short break. Okay. So you're given the graph between the force and the acceleration. So well, for different cases here, you have a straight line A, B, and C. So this is force against acceleration. How can we find the mass? Well, if we can examine that one, that is just a straight line, and the slope of a straight line is delta y over delta x. in this case though, that y is force. So that means that that is just the delta of F, the force, and this one here, the acceleration, is your delta x. So this is delta A. So if you can see here, is it not that F over A, if we're gonna go back to our second Newton's law, so by comparison, second Newton's law tells us that this is MA, and if you're gonna divide F net with A, that gives you the mass. So therefore, the slope of a force against acceleration gives you the mass. Mass of the object is the slope of a force versus acceleration graph. So this is F versus A graph. Okay. So example number 9. In a three-way tug of war, teams pull on a rope with the following forces. So you're given F1 as 30 newtons east. Second one is 20 newtons north. And F3 is 15 newtons west. So we need to determine the net force. So we're trying to get the net force of the rope. So net force is just the sum of all the forces. So that means that I'm adding F1 plus F2 and then F3. So F1 plus F2 plus F3. Again, the sum is just the net force. Again, net force is just the sum of all the forces. So graphically, if I'm gonna show that one, so again, we can represent east is going to the right. So this would be my F1. F2 could be written to the north, that's upward. And west is to the left. So this would be your F3. So F1 therefore, so again, to draw the vectors, you start with your F1 that's going to the right, it's east, that is your F1. F2 is going to the north, and that is your F2. And then F3 is to the west. So to the west, that would be to the left. So it's around 50 newtons. So it should be longer than your F1. So it doesn't have to be very accurate, but it should represent at least the representation. Like in this case, F3 is longer, should be longer than F1 because F1 is only 30 newtons and F3 is 50 newtons. So now, remember that the net force is drawn from the tail of the first vector added. So therefore from here towards the tip. So therefore this is my net force. So this would be my net force. Okay. That should be my net force. And again, this is my net force. This represents my net force. So graphically, I can represent that one, that my net force is lying on the second quadrant. Okay. So if you can remember, we use the in solving for the net force, we use the component method. And for the component method, we try to break down each force to its x and y component. Okay. So for F1, automatically y is 0 because you don't have any y component on your F1. It's lying along the x-axis. It's to the right. So therefore, this is positive 30.0 newtons. And then F2. F2, again, we try to break down to its x and y component. It's north So therefore, that particular, well, if you can also see in my diagram, it's pointing upward. So x is 0 there. This is 20.0. Newtons. And again, this is positive because upward, again, we use the Cartesian coordinate system, that upward positive and to the right is positive. And then you have F3. F3, therefore, again, you have X and Y component. And in this case, your X component is negative 50.0 Newton. And that is negative because it's to the west, so opposite to the direction we're in, we set as positive value. And the Y is 0. Okay. And the next thing that you're going to do is you take the sum of all x's and the sum of all the y's. So if you can see here, for the x's, you have positive 30, then plus 0, then plus the negative of 50.0 Newton. Okay. So the sum along the x is negative 20 Newtons. And summation along y would be, for the first one, it's 0, plus positive 20.0 Newtons, and then plus 0. So if you're going to take the sum, that just gives you positive 20.0 Newtons. Okay, so that also somehow agree with the drawing that we have, that it should be in the second quadrant. So negative x, if you can see it, negative x, positive y, second quadrant. Second quadrant. So therefore, our representation, or at least the drawing that we made here, is somehow closer to the actual. Okay. Although this is just an approximation, but that approximation is relatively close to the real value. Well, after taking the sum, we need to get the magnitude. So the magnitude is just the magnitude of your R, or the resultant force, is just the square root of summation of x squared plus summation of y squared. So that is just the square root of x is negative 20. But if you can see here, regardless of if it's negative or positive, still it should give you an answer, positive value. So if you're going to take that one, that gives you 28.3. So that's the magnitude. That is still the magnitude. So this is not your final answer. So for the direction, so let's say, for example, I'm going to take the, again, when you get the direction, you should base it from your, the tail of your resultant vector. So again, in this case, you're talking about this block line. So let's say, for example, your theta is this one here. Okay. So solving for theta would be tangent inverse of, well, the opposite side is your y, the adjacent side is your x, so summation of all the x's. Again, where did I get this one? Well, if you're gonna draw just a line perpendicular to each other, so this is your summation of x, and this would be your summation of so this would be the summation of y. So if you have this triangle here, that triangle there, so opposite is summation of all the y's, and then the adjacent is the summation of all the x's. So solve for that one, that would be tangent inverse of summation of y, 20 over 20. So that should give you an answer of 45 degrees. 0 degrees. So therefore, the final answer should be So the net force would be the combination of your magnitude and direction. So that would be 28.3 newtons, the magnitude, and then 45.0 degrees north of west. So this would be the final answer. And yeah, it's 45 degrees north of west. Or sometimes if it's 45 degrees, you just say north of west. That would be acceptable, or even west of north, because anyway, it's just in the middle between north and west.